Hello and welcome to my class. I'm Grolin Annalisi from ThinkMo Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is dynamic routing, EIGRP theory and experiments. Before the official start of class, let me start with the unfinished part of the last lesson about static routing. Tell everyone. Then talk about the dynamic routing part and the first dynamic routing protocol. It is also a routing protocol proprietary to Cisco, EIGRP. Do you guys remember this topology? We've covered this in the last class. And the interconnection of 3 devices is also finished. Here we have not configured. This corresponds to the last part of the static route. That is load sharing. Let's first look at this picture. There are now 2 devices. There is a network segment behind the RB. 8.8.8.8. Everyone can see. Here in RA there are 2 lines. Can reach this network segment. Look in the routing table. Has 2 next hops. One is the address of this interface. One is the address of the interface below RB. That is, we have 2 next hop addresses. Go up and go down. Can reach the same destination network segment. We talked about the principle of adding tables to routing. If it is the same routing protocol, we will compare the value of cost. But static routing is different. If the management distance is the same goes for routing metrics. Then both routes will be placed in the routing table. This is what it looks like in the picture now. Load sharing. When data is forwarded, 2 routes can take effect at the same time. Let's finish this experiment now, because there are some leftovers from the last class that I didn't do. Let's turn the device on first. During the opening, let's look at this picture. I added 2 switches in the picture. When everyone is doing experiments after class, also try. Let you touch the device first. That is, when you add nodes, just add a second layer here. When selecting an icon here, choose this. It doesn't need any configuration. Just put it here. I have entered the planned network segment on the map. Let's take a look at the situation today. It starts up a little bit slowly. Let's review first. If I want to configure it, we first under these 2 interfaces, configure the address. Then on the router on the right, configure a loopback port address. 8.8.8.8. A host route with a 32-bit mask. OK. Now we start configuring. Open them first. On the left is R7. I give it a name. It is slightly slower. If the device is turned on after, everyone must remember. You need to name the device first. Because for many simulators, inside is the same. When you have too many devices, its name will be cumbersome. So I just type them in as R1 and R2. OK. After we rename these 2 devices, we'll enter the interface. It is configured with an address. I put a screenshot of this image above. Let's do an experiment. In this process, just look at my configuration. This is basically the same as the previous static routing. So there is no need for everyone to practice after class. Enter the 00 interface. The address we assign to it is 10.1.1.1. Then enter the 01 interface. That is the following network segment. 20.1.1.1. Then the R2 device. .1.1.2. Finally here. Give it up the address of a loopback port. The address of the loopback port is 8.8.8.8. Here to remind everyone. If you up a loopback port, you do not need to manually shut down this interface. It is enabled by default. We can check. Show IP interface brief. Let's check the status of the interface. You can see. The loopback interface is now enabled by default. It does not need manual shutdown. A classmate once asked me a question. When typing the command, what does this BR mean? You can view some brief information about the interface. For example, if you only check the IP interface here, it will be more informative. So if you want to just see a summary, or say you want to just look at some output, you want to add this BR to the current list, called brief. Here are some configurations for the base of the two devices. After the interface is configured, we're going to test the direct connection first. This is the eternal truth. Test 10.1.1.2. That is, test the peers to see if they can communicate. Same. I will test 20.1.1.2 again. Make sure that the directly connected interfaces on the two links are not misconfigured. I hope now. From the router on the left to 8.8.8.8. So how many routes do I need to enter here? If I want to implement a load sharing, how many routes do I need to enter? Okay. I need to enter 2. We first need to enter configuration mode. Remember how to configure static routing? IP route 8.8.8.8. We go to a loopback address like this. This is an exact host route. The next hop is 10.1.1.2. Then go up now. Similarly, I will enter another next hop. 20.1.1.2. I configure them. After configuration, we can view it on the device. Show IP route. Look at the routing table. This achieves the same effect as before. For static routing, if now going to the same destination, the next hop is now specified. And do not specify other parameters. It is load sharing by default. We can test it now. For example, I am here to ping 8.8.8.8. Okay. It is able to communicate. Then we use tracer out. Give it a track. Let me tell you first. If you want tracer out to be faster, you need to turn off the function of domain name resolution here. You can remember this command. No IP domain. We enter configuration mode. You must turn off the function of domain name resolution. Otherwise it will be slightly slower. After closing, we start traceroute. I now wish to trace 8.8.8.8. Then go to check. Which nodes will it pass through? I'm now back to my daily order. For example, I'm going to traceroute it now. If using traceroute, what parameters is it based on? To complete such a function? That is, which parameter does it use? For example, it uses an ICMP message. But which parameter it ends up passing? To achieve this one-by-one tracking effect of nodes, based on the TTL value of the 3 layers. When I send a message equal to 1. Go back. Send a message equal to 2. Go back. Can track the nodes that can be reached now. This is what we call traceroute. Let's trace 8.8.8.8 now. Let's check. For now, if you enter the traceroute command, actually there are 2 ways to go. It will all finish showing. I just make it show a. For example, I enter a 1 here. This means that when I traceroute, returns only 1. Traceroute has 2 functions. In addition to being able to track all the equipment along the way. In fact, it can also do a multipath detection. For example, there are multiple paths to the destination. It is possible to conduct a detection. But we are here. Enter a value to have it return only 1. Let's say when I first type, it returns 20. The second time is 10. Every time I'm doing the next probe. That is, I want to see which addresses I can go to when I arrive at my destination. It actually recurs. The appearance of a loop means that the packet is now going like this. A message goes up. A message goes down. It is when the message is detected. Packets are also loaded. Go up first. Go down. Means that the 2 paths are equivalent. It's different every time. Actually, this realizes the load sharing of data. But in addition to load sharing is not enough. Often multiple links in addition to such sharing. There is another need. Route backup. Also known as floating routing. There is a scene on PPT. But let me tell you another scene. That is, in the current enterprise network, a more common form. This picture shows 2 devices. It's still the same experimental scene as before. Then I hope. Make the above line the main line. Let the following line be used as a backup line. I'll draw a picture for you to illustrate. This is in our actual work now. When will we use such a technology? Let's talk about an environment where companies export. For example, now the following device. As a gateway for the company's exports. The company's export equipment must handle the business of the operator. For example, if you want to browse Google or WeChat, the connection here is the operator's network. Often for companies. When we handle broadband business, we'll not handle only 1 line. Because it's called a single line. A single line is prone to a single point of failure. If there is a problem with the interface between the operator and me in the future, or there is a problem with the interface of this export device, or there is a problem with the line I handled. In short, it may cause problems with the current line handled by the company. For the current internet communication as a whole, this situation is very dire. For example, there is a switch below. Switches may be connected to other switches. There will be a lot of end users waiting to go online. Our daily overall business traffic all go through the company's gateway exit. We all rely on it for access on the internet. Then all traffic. In the end, if they all converge on this 1 line, then think about it. If there is a problem with this line in the future, then the whole business stops. We're going to draw another line here. We often handle business with multiple operators. But I got 2 broadband. Definitely not all high bandwidth. Because it's too expensive. So often we will choose to do 2 different. For example, the one on the left is 500 M. The one on the right is 200 M. The main daily business is on the left. When all employees communicate on a daily basis, traffic goes to the left. Then if one day this line is broken, we'll take the alternate route. The spare line bandwidth can be smaller. Because it's a backup. The backup will only be used if there is a problem with the main line. Then I don't need to spend such a high price to keep it. Just a little cheaper. Although the bandwidth is small. But when we cut to the backup line, can give some time. Repair and salvage of main lines. This is its actual application scenario. Certainly. When the main line is restored and can be used, we will also choose this route for forwarding. This picture is a little bit simpler. No scene drawn. Only one configuration is drawn. But the meaning is the same. Put it in this picture. What does it mean? For example, I made this line into a main line. This line becomes a backup line. Now two routes added to my routing table. But adding it to the routing table means when data is forwarded in the future, two routes are equivalent. The traffic above and below is loaded. Assuming that the above bandwidth is relatively large. 500 M. Suppose the following bandwidth is 200 megabits. The daily traffic will follow the above route. If something goes wrong with this line, go down this line. That is, I only want this route to be added to the table. When we looked at the routing table just now, in this position, it is a fully consistent route. Remember what those two numbers represent? We talked about when the administrative distance and routing metric are consistent, multiple routes will be added to the table. Equivalent routing. On behalf of them when forwarding data. Their abilities are the same. I now hope that the above route will lead down first. Because I want daily traffic to go above. Then how do I? Can it control the routing? For example, I wish now. Daily traffic only takes the above route. Do not follow the route below. We can choose to add the above line to the table. And the following lines are not added to the table. So how to control it without adding a table? You must remember a word. The best path is always stored in the routing table. Only when the path is not comparable. Like this situation. Administrative distance and routing metric are exactly the same. We will add. Now if I want to artificially control an appearance, remove it from the routing table. What method should I choose? Think about it. Only if they are exactly the same. Both routes will be added to the table. I now hope that there is only one route plus table. I can change these two parameters. Let another route not add table. But for static routing, administrative distance is 1. This is generally not modified. We only modify the routing metric. That is, we can adjust the routing metrics by. Then let another route lead down from the routing table. Forwarding only on the main line. Here is a sentence. Floating routes in the case of failure of the main route in the network will be added to the routing table and undertake data forwarding business. That means every day there is a route that does not add a table. This route is called a route backup. It has a name. Floating route. When routing table, we can control it. Control routing addition table. For example, the default administrative distance for static routes is 1. If we modify, I want the above route appear in the routing table. The following route does not appear in the routing table. Then if I modify the administrative distance, how much should I change it to? You have to remember. Smaller is better. So if you want to have multiple static routes, let a certain link or a certain route. Choose it first. Then we can choose. Increase the administrative distance of other routes. We can accomplish such a situation. So let's do it. I am now viewing the configuration just now on R1. I teach you a command called show running config. I'll check it out. Now included in the configuration just made. What are the configurations about routing? IP route. Okay. Here are two routes. So since we want this preference, we just hope this one goes down. So, I want to be in configuration mode. Cancel this route for it. No. And copy it over. Now this configuration has been cancelled. After cancelling, we reconfigure. That is, reconfigure the route just now. But after the configuration is complete, we can put a question mark in the back. Enter a distance metric in this. Is the administrative distance of this route. We can be here. Modify the administrative distance of this route. 1 is a default value. I want it to be greater than 1. Because it is greater than 1 it is not good. The smaller the management distance, the better. So I'm assuming to change it to 2. What is written in the PPT is 100. But it doesn't matter. Greater than 1 on the line. I changed it to 2. Let's still check the configuration just now. Now, when I'm doing routing check, we'll find there is no number behind the first line I configured. Because it defaults to 1. Default is not displayed. The management distance in the second one is changed to 2. Everyone can guess. Now for the two configurations. Its administrative distance is different. Then according to the principle of adding table we thought before, when all destination networks are the same, we'll trigger the comparison. Now they are both 8.8.8.8. 32-bit mask are the same. The destination network and mask are the same. We'll trigger the comparison. Then we first compare the administrative distance. So when we compare now, smaller is better. So, 1 is 1. 1 is 2. Obviously the first one is better. If the first one is better now, the second item will not be added. Let's look at the routing table now. Its next hop is only 10.1.1.2. It will not be added to the table. So for two routes, now its administrative distance is not the same. The principle of adding tables. We'll select an optimal table addition. So there will be no other route. But that's just saying. Now only one route appears in the routing table. Then according to what we just said, this situation is drawn in this picture. How can this line complete a switch? That is our scene. The reason why one line is the main line. One line as backup line. It is hoped that the daily traffic will take the main route. If the main line fails, take the backup line. So how can we let the main line fail? Very simple. I just need to enter the interface. Just shut down the interface for it. Let's say I'm on the device on the left. Our interface to the main line. Then give it shutdown. Then once I shut down now, we can observe the phenomenon. Excuse me. Is the route still there? Let's check. The route just now is gone. Now the next hop that appears in the routing table becomes 20.1.1.2. That is, becomes the address of this interface. Now the traffic goes the following route. Why once this interface is gone, the corresponding route disappears? For routing, if the physical state of a port is up, then the corresponding direct route exists. Remember the direct route we talked about earlier? That is, this interface is configured with an IP and no shutdown. The peer also has an interface. It means that the physical state and the protocol state are both up now. A direct route will be generated. This is what we said before. The physical state of the port is up. Then the direct route exists now. Then if the physical state is down, actually, This interface is not working. Then the direct route disappears. So for the current environment, because the ports are down, there is no such direct route. Its next hop is of course unreachable. So this route is correspondingly gone. Because now the next hop is the direct connection. Then this interface is actually down. If there is such a route in the routing table. Future visits. I can't forward it. Because the interface is gone. It doesn't make sense. Let's test it now. For example, I ping 8.8.8.8. Still works. Because the route must go the following route. Then if I restore this interface now, will it retable? Okay. It will be relisted. Because if the route comes back, to retrigger the comparison again, we can verify. For example, I entered the 00 interface. I turn on this interface, no shutdown. I hope it pops up some log messages later. Okay. Finished playing. Let's check now. IP route. Okay. Now in the routing table, the next hop becomes 10.1.1.2 again. That is, it's on the line again. Route restored. So we will now find if when this interface is enabled, the next hop in the routing table becomes the main line. If this link fails, then the next hop in the routing table becomes a backup line. So, given that we have defined the administrative distance, in fact, as long as the main line does not fail, it is forwarded normally on a daily basis. If it fails, go the following line. If it recovers, go the above route again. So this route about 8.8.8.8 in the routing table is always changing. That is, according to the current real forwarding situation of the main line. If it creates problems, it just sinks. If it's okay, it resurfaces. So we call such a route a floating route. Usually, it's actually called route backup. It is a backup technology. I now have an extended question. For example, now this interface is all fine. But if you get into this device, I put it on the interface, and if it is down, do you think I can ping now? We are now on R2. Enter the interface of R2. 00 interface. Shut down. I now down this interface. If I look up the table on R1, how much is the next hop? I repeat. If R1 goes to 8.8.8.8, the next hop is this interface. So we just verified. If I put the router on the left, this interface is down. The routing will switch to the following line. If this interface recovers, just go the above route again. That is, regardless of whether the interface is down or not, can be pinged. If it is down, switch to the backup line. My problem now is, this end of the line is fine. But if the interface on the opposite end is down, the flow cannot be switched now. Because I'm already shut down now. Okay. Let's verify. Actually, let's see if the routing of R7 is correct. I'll check it now. Show IP route. You will find, obviously, the device on the right. Enter the 00 interface. Already shut down. And now this state. It is indeed down. Then why is the next hop here still 10.1.1.2? This interface has been down. But for the device on the left, it does not know that the interface is down. Its current next hop in the routing table, still this interface. Then the future data will go to 8.8.8.8. It will still forward according to this interface. But now there is a problem with the physical state of this interface. Then data traffic is sent. It is impossible to receive. So you will find, if there is a root, it will receive the data. If no root, it directly lost the data going to 8.8.8.8. There is now a local root. It checks the routing table and forwards to the next hop. There is now a problem due to the next hop. Then actually, data here. It is impossible to receive. So, there was a problem when data was transmitted on this link. This phenomenon is called routing black hole. When a data arrives on a device now, this device obviously has a route to the destination, and also perform data forwarding on the data. But the data didn't reach the destination. This phenomenon is called a routing black hole. When you learn BGP in the NP phase in the future, we'll touch it. This is a very typical phenomenon. What we are talking about today is also called routing black hole. Do you know how to solve it? Certainly. NA stage will not talk about this thing. I just want to mention, we will learn a little tool in the future. It is a link detection mechanism of Cisco, called SLA. This will be learned in the NP phase. Now the problem is that this interface is down. But this device is not aware, since it has no way to perceive. So it has no way to know that the interface is down now. That's why I added a switch in the middle. Direct connection of devices is also called direct connection. Actually, it has two cases. A direct connection in the physical state. That is, there are no other devices in between. The inner end of the interface of one device is the interface of another device. This is called direct connection in physical state. For the R7 and R8 we talked about today, a switch intervenes between them. This kind of direct connection is called logical direct connection. The switch does not affect the real data forwarding, but it affects them not being directly connected anymore. This interface is down due to the intervention of a switch in the middle. This interface cannot perceive that it is down. If they are directly connected, it's down. This interface is also down, because this interface can directly sense that the peer link is down. This link is no longer available. But because a device intervenes, it is imperceptible. So we will learn a method in the future. Let R7 perceive that the 00 interface of R8 is down. Then switch the route to the following line. Rely on the technology of SLA. This is a Cisco link detection mechanism. The device on the left keeps sending messages to the device on the right to detect the carrier a nature of this interface. If it works, we'll reply to the device on the left. Then finally bind the SLA to the above route. That is, bind the SLA to this route. This is the route of the main line we are using now. In the future, through a detection mechanism such as SLA, to detect the other party's interface. If the peer interface is down, then the SLA is down. Since it is bound to this route, then this route will be down. Down means to come out of the routing table. It no longer does normal data forwarding. Then the following line will reappear in the routing table. That is, I pass a detection mechanism. Check the status of the other party's interface. If the status of the peer interface is down, SLA will be down. Due to the SLA and this static binding, then this static route will also be down. Then if this static route is down, let's go back to our original idea. If the above line is down, the following line will float to the routing table. It is also a floating static route. Let's not talk about this configuration now. Only in the NP stage. But you need to know this. Okay. Let's move on. Default route. Actually, I told you before. For current equipment, RA wants to reach the network segment behind RB. You will find it has entered 3 network segments here. Then in theory, if I configure it here, how should I configure it? IP route 192.168.1.0, 3255 and 10. The next hop is 12.1.1.2. This is the first. If the data wants to go to 2.0, IP route 192.168.2.0, 24-bit mask. The next hop is also 12.1.1.2. The third is the same. You will find, as long as this network segment is behind the RB, which network segment does the data actually go to? The next hop is the left interface of RB. So traffic will be sent to RB anyway. For this case, we can enter a default route. It is represented by 4 zeros. The next hop points directly to 12.1.1.2. That is, as long as the data goes to any place in the future, can send traffic to RB. Of course, the premise is that there is no precise route in the routing table. For example, a route is now entered in the routing table, 192.168.1.0, 24-bit mask. Then if there is a route to the 1.0 network segment, it will match the following. Does not match the above. I should have told you about this in the last class. Let's take a look at its configuration. IP route. For example, I now simply configure a route for it. 0.0.0.0. The mask is also 0.0.0.0.0. Suppose the next hop is 10.1.1.2. Okay. Let's check. Just check the status. There is now a default route in the routing table. The reason why I entered this command for you. I want everyone to see this phenomenon. That is, the form of the default route. In the routing table, it will be denoted by an asterisk S. When none of the routes can match in the future, match the default route. So where is this thing most used? I give a simple example. For example, on PC. PC has a default route. We can check it out. Route print. There is now an IPv4 routing table. The host also has a routing table. Now the mask is 0.0.0.0. The reason is not 4255. Because there is a longest mask matching principle. 0.0.0.0 represents all routes in the entire network. Then the next 4 zeros represent any mask. There is no restriction on the network segment. No restrictions on masks. Because it is the combination of IP address and mask. To define the network segment. Now it can be any network segment. For address and mask are not matched. Including when we go to match in the future. The mask is the longest to match. If now the mask is 4255. It's 32-bit. Then send any piece of data. It must match the route. Default route forwarding. That's wrong. Because 4255 are 32-bit masks. For equipment, it's also 4 zeros. There is a gateway here. The data is forwarded. Now your computer can access the internet. Thanks to such a default route. Other than PC. It will also be used on the company's public network export. Let's say this is the company. This is the operator. Then I want to access all the data on the public network. Such as Google, YouTube, Facebook. They are all public network services. Available through the operator. Forward the data. In company export here. We'll enter a default route. Point to the device that the operator connects with us. That is, in the future, no matter where your data is sent, The traffic is handed over to the operator. Let it help forward this default route. It is a default route that every company export will have. As long as the company is now using the internet business, there will be a default route. The next hop is pointing to the operator. The export is configured like this. For export, it's just a device. Its configuration is IP route 0.0.0.0, 0.0.0.0, Internet address of next hop carrier and company. Generally speaking, this internet address configuration is the company side and the operator side. When handling carrier business, it will provide the internet address. If the future uses dial-up internet, such as the form of PPPoE, then it is another form. Then the exported IP is not fixed. If the enterprise handles fixed bandwidth, if there is a public network IP here, there is also a public IP here. Now the most used is a 30-bit mask. That is, only 2 addresses are available under the 30-bit mask. One end for the company. The operator at one end uses just use the next hop to point to the operator. As for how to get back the operator data, we can't talk at this stage. The future IE stage will talk about. A default route points to the past. Don't worry about how it came back, because this is the configuration of the operator. For business, when configuring, it is to export a default route pointing to the internet address. This address is when doing business. The operator will provide. Okay. Let's summarize the problem of static routing next. When we were configuring in the last class, everyone will find a problem. The overall configuration of static routing is very complicated. It's not that its mechanism is so complicated, but the input on each device is complex. Let's take them as an example. These 3 devices. If I want them to be able to communicate with each other, that is very troublesome. Let me introduce to you, based on our configuration from the previous lesson. In fact, only 3 PCs can communicate with each other. If you have tested other, you will find R3 goes directly to ping R5. It doesn't work, because R3 does not have a route to network segment 23. That is to say, R3 can ping the device. That is because it has a route to 192.168.3.100 on it. But it can't ping the left interface of R5, because it does not have a route to network segment 23 now. If you want to ping the address of this interface now, or ping the right interface of R4, you need to enter another default route here, pointing to the 23.1.0 network segment. All I want to say is, we just let the 3 PCs communicate with each other. I'm going to be on this device. Both the 2 network segment and the 3 network segment must be entered. I want to enter 1 network segment and 3 network segment on this device. Enter 1 network segment and 2 network segment on this device. You will find I have to do a lot of configuration for each device. Secondly, after configuring, it's just 3 hosts communicating with each other. These network segments are still unreachable. So you want to pass the static route. Ping all 6 devices in the whole network. Relatively complex. There are not many network segments. That's it for configuring static routing. In the future, if in the configuration process, more equipment, it means that you want to connect the whole network. It is very complicated to use static routing. And it's easy to go wrong. And you will find halfway maybe on a device, the configuration of a static route is missing. It may cause a certain device to fail. Suppose there is a 1.1.1.0 network segment here. One day this network segment disappeared. You don't have to worry about how you disappeared. This device may be gone. The business has changed. There is no such segment here. Then I'm going to be on each device. Cancel this network segment information. There may be many routers in the future. You can't say that. This network segment doesn't exist anymore. Static route is still. If a piece of data arrives, it cannot be forwarded. There is no route at the peer end. Have to cancel. So it's a hassle. This is cumbersome from a configuration point of view. Of course it depends on the demand. If you only let the PC communicate. In fact, it doesn't matter whether the middle is connected or not. It does not mean that the host cannot be pinged. Because they do not belong to the same network segment. The specific network segment to go to cannot be reached depends on the routing table. Instead of looking at the middle of these. Although the data is forwarded through this link. But it doesn't mean. It must be possible to ping the device from here. The data is just passed through. It helps to retweet. As long as this packet arrives on this device. Know the destination network segment. The above are some disadvantages of the static routing we mentioned. The first problem is that if the network is large, the configuration is relatively cumbersome. Another problem is static routing is a very dumb routing. Because static routing, it is impossible to perceive the overall network changes. For example, multiple devices are now interconnected. Connect each other with a line. Now pointing one by one statically. Suppose there is a network segment on this device. Is 1.1.1.0. One day this segment disappeared. If you are not in time on every device, cancel this static. Then it will forward the original. That is, as long as you don't cancel. It always thinks that this network segment is still. Then it means, no matter how a remote network segment changes, the equipment here can't sense it at all. So you have to manually configure. All information can only be maintained manually by the network administrator. Then it is relatively cumbersome. Then the corresponding dynamic routing. It can solve this problem. If a network segment already exists in the overall network topology, in the future, this network segment will disappear. It can automatically tell other devices. This is the difference between them. That is, only preconfiguration is required. In the later stage, all their information can complete automatic interaction. This is the biggest difference between static routing and dynamic routing. The difference at the configuration level. In fact, it's better to solve. Because now for the project. Actually, the configuration of many projects at the beginning. It's all configured automatically. Our templates. And change it inside. Including what we'll talk about shortly. We will have corresponding SDN controllers like this. We can send configuration to downstream devices. Even post the phenomenon. All okay. So although the configuration is cumbersome, but actually, the biggest difference between them is not in the configuration, but in the perception of changes in the network. That is, in the future, when our network changes other than whether it can be updated and maintained automatically is the most important thing. Because we don't want, after a network is established successfully, have to stare at it every day. Adding or deleting a network segment requires manual configuration of dozens or even hundreds of devices. This is too exaggerated. So that's one of its downsides. We're going to learn another form of routing next. Dynamic routing. Both static routing and dynamic routing are a method of adding routing table They are used to calculate the routing table. There are direct and static routing tables. There is also a dynamic. In a larger network, we can use dynamic routing. Automatically sense network status changes and network topology changes. This is another form of routing table construction. Let me tell you about the concept of dynamic routing. By running some corresponding protocols on the device. These protocols are some dynamic routing protocols. The process of automatically exchanging routing information through this protocol. Dynamic routing. That is, just need to run some kind of protocol on the device. Automatically exchange routing information through this protocol. This is called dynamic routing. There is no algorithm for static routing. It only relies on human configuration. And dynamic routing has an algorithm. This is a difference between them. The concept statement mentioned on the PPT is more official. Generated by interactive routing information. And maintain the routing table required by the forwarding engine. It is the routing table when data is forwarded. Admins don't need to be like static routes. Manual maintenance. Run a routing protocol on each router. It means at least 2 routing protocols. It is called each. If there is one, it will not be able to run the routing protocol. Because a routing protocol is not a router. A routing protocol requires at least 2 routers. It doesn't make any sense to turn on a router. It has no way to exchange messages with other devices. If a company only has 2 devices, usually go static. So actually, dynamic routing protocols are considered for medium and large enterprises. If it is a small business, just a router, there is no use for this thing at all. We need on both routers. Run the same dynamic routing protocol. For example, run a RIP protocol on the left. Right running an OSPF protocol. There is no way to establish a relationship between them. There is no way to learn routing from each other. Both of them must be the same dynamic routing protocol. So at least 2 devices. The protocol running between the devices must be the same. Otherwise, there is no way to learn through a certain agreement. You will learn later. For some medium and large networks, multiple routing protocols may be running at the same time. It's also possible. It is possible to run both. For example, EIGRP and OSPF are used together. It's all possible. But we don't need to think about those now. Because those are related to network architecture issues. Just run the same routing protocol at this stage. Let's go on. Routing protocols have some corresponding features. Maintain routing information. It's just some updates and maintenance in the later period. There is another one called determine the best route. Let me tell you about this. There are now 2 devices. An OSPF is running between the 2 devices. So now suppose there are 2 paths to go. We run an OSPF. OSPF has an option value. What exactly is the best route? Which route is better? Now that the routing protocol is consistent, management distance is definitely the same. If we compare, we'll only compare routing metrics. Then, for such a value, it is calculated differently. OSPF selects the best route based on bandwidth. Suppose the line above is 10G. The following line is 10M. Then it will choose to take the above route. Because the upper band is large. This is called determining the best route. After determining the optimal path to any destination. Actually, the best route is calculated. Then next, the routing table will be built based on this information. Same destination network. For example, I learned a 1.1.1.0 network segment here. An OSPF is running between the 2 devices. Learned one thing from OSPF. Run another RIP. I learned a lesson from RIP. Also running an EIGRP. Another lesson learned through EIGRP. Then finally compare the administrative distance of the three routing protocols. You can also choose an optimal addition table. Is to create a routing table. So it's all a process of comparison. In the end, a static route kills all dynamic routes. Because the static administrative distance is 1. Lower than all dynamic routing protocols. Static routing is not only used by small businesses, medium enterprise, large enterprise, including current operators are using. Because the dynamic routing protocol has a fixed principle of routing. Just like the OSPF I told you. It's based on bandwidth. Suppose the above line is 10G. 1G for the following line. Always go above. Never go below. For example, future data will go to the destination network. Very much traffic. Traffic will be congested. Because now there are two lines. The following 1G line will never go. That is, if the network does not fail, never go the line below. Will cause all traffic to go only above. At some point you'll find out. If the concurrent network traffic is too large, it will cause the above overall link bandwidth resources to be full. But the following link is idle. This is often. At that time, we can enter static routes in a targeted manner. For example, which destination network segment will the future data go to? Let this part of the traffic flow downward for traction. That is, the combination of dynamic routing and static routing is also very common. Don't understand that static routing is no longer needed. Not only small businesses use static routing. It is a controllable mode of operation. Okay. Let's see how to update. There are two ways to update the dynamic routing protocol. A cycle update. A trigger update. Periodic update. I still use OSPF as an example. Because EIGRP has no periodic updates. So I can only use OSPF as an example. This is R1. This is R2. Two devices. A PC is connected here. This is also connected to a PC. There is a line between them. Another dynamic routing protocol is running between the two devices, called OSPF. You don't care how it works. The two of them can now interact with data. For example, there is a segment here. 1.0. There is also a segment here. 2.0. They have learned from each other. R2 can go to 1.0. R1 can also go to 2.0. After learning, it is equivalent to the stable operation of the routing protocol. The message is all over. They also periodically send messages to each other's devices. Send your own routing entries. OSPF is 30 minutes. Because it is necessary to make sure that the overall information is consistent now. This is called periodic update. Periodically send your own route to the other party. But we have a problem here. If now in the entire network environment, only periodic update. For example, at some point, a 3.0 network segment came to R1. Then 30 minutes later, R1 only told R2 the network segment of 3.0. This is too slow. Added this network segment from R1. Until R2 can finally identify and learn this network segment. 30 minutes passed. After so long, I might as well enter a static route. So say you will find 30 minutes is unbearable. Certainly. I just give an example. You should know. 30 minutes is too long. So OSPF is definitely not like this. If it is like this, this deal doesn't work at all. So in addition to periodic updates, it also has a way to update. Trigger update. Parallel between the two. Trigger update is OSPF will periodically send messages to other devices. Of course, it is not sent directly to the device. It uses a multicast method. Other devices will receive messages periodically. It is a triggered update. As long as there is an extra network segment on it now, it will tell other devices that there is an extra network segment on it. Besides, it will be updated periodically every 30 minutes. This is what we're talking about as a parallel between the two. EIGRP is not used much. It has a constraint. It is a proprietary protocol of Cisco. Publicized in 2013. Public ownership means that others can use it. But it costs money to use. So we don't. This is one. Secondly, spending money is not a buyout system. Is a subscription. That is, we can't use this protocol forever. Have to buy a few years. Equivalent to buying authorization. This agreement is excellent. But because it costs money. So we don't. Before it was made public. If you want to use this protocol, all must be Cisco equipment. That is, your networking environment cannot have equipment from other companies, because other devices do not support. So it didn't hit the market at all. Very low occupancy. Very good technology. But no one used. It's really a pity. But we learned Cisco. EIGRP must learn its mechanism. Although it is not used much now. You hardly ever see EIGRP on projects. But don't give up your interest in learning it. These are the two update methods of OSPF. Then, for EIGRP, only triggered updates. No periodic updates. Because in fact, there is no need for periodic updates. In addition, when at some point this network segment disappears, the device will immediately tell other devices that its network segment has disappeared. Other devices quickly delete the information about this network segment in the intersection table. Don't visit it anymore. Because its network segment is gone. This is called trigger update. Triggers real-time updates of updated assurance information. Periodic update ensures the overall information interaction of the routing table. OSPF is once every 30 minutes. Ensure absolute synchronization of information between devices. Here are some differences between the two update methods. But these two update methods, not every routing protocol has. Just like EIGRP only triggers updates, while OSPF has both. Look at the specific agreement mechanism. Next, let's learn about the types of dynamic routing protocols. From the point of view of the current algorithm, there are two. One is the distance vector. One is the link state. Then tell everyone. We're going to talk about EIGRP. What kind of agreement is EIGRP? It belongs to the distance vector. It is updated in real time. It is a distance vector routing protocol. But it is a distance vector protocol with link state features. It has some characteristics of link state. It borrows some mechanisms in the link state. Because the development process of EIGRP refers to some public protocol factors. So it has both link state and distance vector. But in the end it's a distance vector protocol. Because when we judge the type of dynamic routing protocol, the specific thing is that it is interacting with the routing table or link state information. EIGRP interacts with the routing table. So it's essentially a distance vector protocol. But it has some characteristics of link state. Let's start with an older protocol called RIP. We won't talk about RIP in the course. Because it's been outdated for too long. Can simply mention. But there is no need to talk about its configuration. Suppose now there are 3 devices. This is 1. This is 2. This is 3. Connect with each other. Let's say there is a network segment here. 1.0 network segment. Then I now want 3 devices running RIP. First of all, you need to know. It is a dynamic routing protocol. It is characterized by. For device 1. It wants to pass this 1.0 network segment. Then first it will learn its own direct route. In addition to the 1.0 network segment. As long as it is directly connected to the network segment. It will learn. Then form a routing table locally. It will pass this table to its neighbor device 2. Device 2 will first accept this table. After accepting, calculate from your own table. Because between them, there may be some directly connected network segments. Device 1 also passed it. It has to calculate to see which local ones don't. The 2 of them are now connected to a device in the middle. For this device, there may be a network segment behind. It also gives device 1 the. It also gives device 2 the. Then device 1 gives device 2 again. For device 2, you have to do the math to see if you have 1. Discard it if it has. Combine with device 1 if it doesn't. Then it will generate a new routing table locally. Then pass this new table to device 3. Device 3 after receiving. Also local first. After receiving. Calculate with your own local table. After the calculation, a new table is generated. The new table is then passed on to subsequent devices. This is a typical feature of RIP. Here is an algorithm for it. It is a very typical distance vector protocol. RIP is not easy to use though. But now there are also usage scenarios. It has long been unsuitable for the current network environment. Because it has a limited number of hops. RIP up to 16 routers. Now there is almost no equipment inside. It is also necessary to specify the number of devices for the scene. Any medium or large network device. More than so many. So RIP is useless at all. This is what we call the distance vector protocol. A typical representative of it. Called RIP. RIP as such a distance vector protocol. It will only update packages periodically by exchanging. To obtain network change information. It didn't trigger the update. It only has regular updates. Or take our example just now. In fact, I have drawn this picture many times over and over again. 2 devices. There is a PC here. If the 2 devices run a RIP, there is a network segment here on the left. 1.0 segment. At some point this network segment disappeared. But since the device on the right now, just learn the network segment of 1.0 from the left. If this PC wants to access the 1.0 network segment, this device also needs to help it forward. Flow here. It still has to give this router. Because for RIP, it is not updated in real time. It will update every 30 seconds. So in the process, the device on the left still needs to continue sending data. So the first question is, it is definitely not possible to send data. Actually, this route makes no sense. So, this leads to the black hole problem we just mentioned. In this short time it will have a black hole. The second problem is a drainage problem. Drainage is, obviously, the device on the left does not have this network segment now. The 1.0 network segment is no longer here. Also direct the traffic of 1.0 to here. For this device, it drives a lot of traffic. The device still needs to process this message. Because now it is going to the 1.0 network segment. Although the device will not process it looks up the table and cannot forward. Drop packets. I have to tear down the second floor first. Look at the second floor and look at the third floor. In the third layer, it is found that the data is going to the 1.0 network segment. And if there is no such data packet in its table, it will be discarded. Then the data will waste the forwarding performance of the device. That is, waste device hardware. It also wastes the bandwidth of this link. You may think, it's okay to waste some of this stuff. In fact, every beginner will have such an idea. But this is not okay for the network. As an agreement, this is a very serious common disease. This is absolutely not allowed to exist. Because it is a protocol. It is necessary to consider various optimization problems in the network. RIP optimizes every small link. Very poorly done. So this agreement is now gone. Of course, it is still configured on the device. But this thing is useless. Finally, let me briefly talk about horizontal split. I draw a picture to explain. Next time you see this word, it should also be the time to learn BGP in the NP phase. You will touch this split horizon again. I give a simple example. Now 3 devices, interconnected with each other. Assume that the RIP protocol is running in the middle. You don't need to have a deep understanding of this protocol. Now this has a network segment. 1.0 segment. Now device 1 wants to pass this network segment information to other devices. Suppose pass to device 2. And also to device 3. I mark it. This is device 1. This is device 2. This is device 3. This is 3 devices. Then device 1 now passes to device 2. Of course, after the local calculation of device 2 is completed, it will also be transmitted to device 3. Device 3 will also send it to device 1. After the local calculation is completed. This is how they pass. Device 1 will also pass its own information to device 3. This is RIP. An ancient mechanism. But it's not actually like that. I just give you a simple example. This information is passed back and forth like this. Then sometime, for the current device 1, this segment may no longer exist. This routing entry may be gone. But before it updates, maybe device 1 is receiving data packets from other devices. That is, it is possible that device 2 and device 3 have been sending data packets to device 1. Because the original device 2 learned the 1.0 network segment from device 1. It may be passed to device 3. Device 3 also gives device 1. At this time, device 1 will know. Because it now receives data from device 3. But device 3 receives it from device 2 here. Device 3 only knows that it will go to network segment 1.0 in the future. So it will find device 2. Device 1 also knows that it will find device 3 when going to network segment 1.0 in the future. Then, for device 2, in the future, if you go to the 1.0 network segment, you will find device 1. Because that's what device 1 gave it. Since the information cannot be updated in real time, and the message is passed back and forth in the whole environment, it will just create a loop problem. Because the information is not updated in time. Then this problem is solved by splitting the horizon. Such an algorithm is very simple. It is the data sent from this interface will no longer receive from this interface. That is, as long as there is a data like 1.0 now, device 1 sends out to device 2 through this interface. Then it will no longer receive from this interface in the future. The data sent by device 1 to device 2 will not be received later. The data sent by device 1 to device 3 will not be retrieved in the future. That is, this routing entry sent by device 1, it will no longer receive. So that solves its problem. This is called split horizon. What we said above is several characteristics of distance vector routing protocols. Let's move on. Some defects of distance vector routing protocols. The first thing to mention is the trustworthiness of routing metrics. For a protocol like RIP, it takes into account its routing metric. Just think about one thing. Hop count. Each layer 3 interface passing through a router is called a hop. For example, there are 3 devices. There is a network segment here is 3.3. I now want to access from device 1 to 3.3. So that's 3 hops. Because the data ends up at this loopback port. This is also a hop count. It considers 3 hops. So now the whole is called cost. Or called metric. Going to 3.3 is 3 hops. But in this case, credibility is low. I draw a picture to explain what credibility is. It's just dictation that's a little boring. For example, here are several devices. Draw a little more average. I draw a few more. For the above equipment is connected like this. The following devices are connected like this. Now write a network segment here on the right device. Still 1.0 network segment. Now run the RIP protocol between all devices. It selects the optimal path based on the number of hops. If R1 visits R2's 1.0 network segment in the future, how many roads are there? Okay. There are 2 roads. So which of these 2 routes does it take? Assuming the above 2 lines are 10M. The following 2 lines are 10G. I wrote bigger. In this case, it can show the disadvantage of RIP protocol. At this point, you will definitely think that this traffic wants to go the following route. Although the above line passes through less equipment, but it's only 10 megabytes. And the following is the 10G link. But unfortunately, RIP selects the optimal path based on the number of hops. Data goes to network segment 1.0. It takes 3 hops to take the above line. If you go down, there are 5 hops. So the following line is bad. The data will choose the above line. The above line looks like a path. The line below looks like a big road. But when the data is actually forwarded, the speed between the 2 of them must be the one below. There are many routers in the middle. Actually take more time. Mostly due to the time for device lookup table forwarding. The device has received data. It checks its own routing table and forwards. This time does go through one more router. Just check the routing table once more. That will be relatively slow. The above is 10 megabytes. Below is 10G. One flow every time. Go here to check the time spent in the routing table. Due to inconsistent link bandwidth, have an overall impact. So for RIP, it is a completely wrong protocol. From the selection of the optimal path. So there is no way for it to continue to be used. The current overall processing age is a bandwidth supremacy. For us now, bandwidth is so important. Now it's all 10G lines. You're a fool to use 10 megabytes. So now this thing is useless. This is called low confidence. Next. There is another sentence. They exchange information by periodically broadcasting the entire routing table. Of course, RIP uses broadcasting in a version. It also improves. Let's look at this routing table first. Actually, RIP is the routing table for delivery. It would be better if the overall network environment is small now. If the network environment is particularly large, it means that the routing table of each device will be very large now. If the equipment is updated periodically, just keep passing the routing table back and forth. I will give you a simple example. Everyone must be clear. Traffic problems during network data forwarding. Suppose now multiple devices. They are connected to each other. What we are talking about: running OSPF, RIP, EIGRP, etc. These things are dynamic routing protocols that generate routing tables to run messages between them. That is, all the content that is interacting in it now, just to generate a routing table for each device. It is only called traffic inside the protocol. The reason we build the network and run the protocol is to allow these devices to communicate with each other and learn the network segment behind. Learning their respective network segments is for let these terminals and some servers behind the network segment. Let these various devices communicate with each other. Routers are only used to forward data. So theoretically the information data transmitted in the link, the data used to generate the routing table, should not be too large. For RIP, it updates the routing table every 30 seconds. On this link, routing tables are sent between them every 30 seconds. Then this link has been running, used to maintain neighbor relationship. These traffics include update routes. It will not be able to run so much normal business traffic. Business flow is: now here is a host. It wants to access a router behind this device. Traffic also goes along these lines. We call it business traffic. We build networks to run business. Then in the network, there should not be particularly frequent traffic exchanges other than business on the link. This is an occupancy issue of link bandwidth. So for RIP, it either selects the optimal path overall, or the way it routes updates are very unoptimized. So it's now obsolete. But there is also a BGP written here. When we talk about OSPF later, let me tell you about it again. In fact, strictly speaking, it is also not a full distance vector routing protocol. It has another name. This protocol runs on the public network. We don't see BGP internally. It is used to run between different AS. For example, if your company is a very large company, to connect with some operators, BGP may be running in the middle. Including carriers may run BGP between. It belongs to an external routing protocol. Next, let's talk about the algorithm of the link state routing protocol, called link state, called LS. A typical link state protocol is OSPF, ISIS. Cisco does not seem to talk about SS, because it is a carrier technology. We will speak OSPF. It will have an NA, NP and IE stages. It's just that the depth is different. For these two routing protocols, ISIS, you just need to know this stuff. They all use the SPF algorithm. It's just that the way it's done is different. You'll think it's pretty much the same inside. But ISIS will be more optimized. It is also stronger than OSPF. Here are some differences between them. The biggest difference between link state and distance vector is that what is sent between them is not the routing table. Instead, link state is sent. This is what I told you. Distinguishes whether it is a distance vector or a link state. It depends on whether it interacts with the routing table. EIGRP interacts with a routing table. So it's a distance vector routing protocol. For link state, let me just expand it for you. The link state is like an OSPF protocol is running between the two devices. Assume that the device on the right has a network segment of 1.0. Then as long as the device. Declare this interface into OSPF. A link state is generated, called LSA. Then this link state is not a routing table. If you wish to generate this state, the device on the right will be passed to the device on the left. But it is not a table. After it receives this information, if it wishes to form a table from this information, it needs to pass the calculation of the SPF algorithm in OSPF. That's what we're talking about. An algorithm of shortest path first. After this algorithm is calculated, form a table locally. I will give you an example. Link state routing protocol. Like giving you some ingredients. If you want to eat, cook for yourself. Distance appetite routing protocol. Like cooking for you. You eat it directly. Here's the difference between them. That is, LSA is like a raw material. Give some info to the device. After the equipment calculates itself, decide how representations are added. Then for RIP. That is, it calculates locally to the device. Take the equipment and use it directly. Including EIGRP is the same. But it is much more advanced than RIP. That is to say, link state information is just a link state, not routing table. RIP transfers the routing table. This is a qualitative difference between them.